Okay, so the recording has started. All right, so um, no student. All right, no worries. So I welcome you all to another doubt clearing or problem solving session for the course Smart Grids, Basics to Advanced Technologies, being taken by Professor N.P. Padhy and Professor Premlata Jena from IIT Roorkee. I am Swastik Sharma. I am a PhD student at IIT Kanpur and I am a TA for this course. So last class we started with so the next few, so whatever we have studied until the last week, uh we're now putting it to a test. Okay, we're now demonstrating how what we have studied could be could be transformed into tangible outputs, like for example demonstrations, and that's what we want to do, right? How would you be able to know that whatever you're proposing is going to work in real life, right? And for that, I told you that there are 4 steps for demonstration or validation. The first step is your software in loop validation, where you simply run it in a simulating platform, like for example an RTDS, Opal RT, or RT Lab, any simulating platform you have, PSCAD, RSCAD, right? And then in second, what we do is, if let's say we are proposing a controller algorithm, let's say controller function, how controller will act, or let's say we are proposing a unique, a protection law or a protection logic, right? So before using that proposition on a real world application, we first check if, let's say, that makes sense, that controller is working perfectly fine through controller hardware in loop validation, where all the network and everything, the power hardware is in our simulating platform, and only the controller is separate, so it's on a hard drive, hardwares, right? So that is called controller hardware in loop validation. Okay, and then if that validation is successful, we move towards power hardware in loop validation, where we simulate by keeping all the the power hardware also in our like for example, if we are proposing controller logic for a converter, or let's say protection logic for a relay, we use it and we do the validation on the real system, right? And if that is also successful, then we are ready to deploy it in any field or test pilot, right? And that is what these demonstrations over the next few weeks will focus on. So today we will be talking about, demonstrating the AC microgrid, DC microgrid, or AC-DC microgrids, and we will see, how these demonstrations are done in real time. I mean, I won't do the demonstration since I don't have the access to that hardware. But yeah, if you have gone through the video lectures, you would know what kind of demonstrations I'm talking about, right? So let me share my screen and then we'll start. Okay, so this is done. Let me just. Hmm. Okay, so this is what the instructor started with this week. So I've already talked in depth about in my last week lecture. I also showed you a very beautiful slide deck, right? It was by my senior here at IIT Kanpur. And there we studied what is software in loop validation, what is controller hardware in loop validation, power hardware in loop validation, and the field validation, that is the last step of our validation, right? So I won't go into it this week, but or today, even in the lecture, but you can always go back to the YouTube lecture. The link has already been provided with you, right? So the first thing that we are going to study today is modeling and simulation of an AC microgrid, right? So what we want to say is how, let's say, we want to propose, right? Yeah. So we want to propose how an AC microgrid would look like and how it will work. So what do we propose, right? A, we want to see that the power flow control strategy or schemes or the energy management schemes that we are proposing for that AC microgrid, will they work in grid connected mode or in islanded mode? right? So what we want to check is, let's say if that we have made an AC microgrid, will it be reliable enough to work in real life, right? So first what we do is we simulate that AC microgrid or whatever microgrid we are proposing virtually. And how do we do that is by doing a continuous real-time simulation, right? And what is real-time simulation? We just make sure that whatever the simulation time period is, it is in sync with the real time, right? Because RTDS use, and for that RTDS uses GPS or global positioning satellite, right, to make sure that the time difference is same in both the cases, right? And that is what continuous real-time simulation we've all discussed, so I won't go in depth today, but yeah. And hardware in loop simulation is nothing but whatever kind of, power devices, protection, converters, whatever we are using, we make sure that we do a hardware in loop simulation as well. As I've already told you, two types of hardware in loop simulation: controller hardware in loop and power hardware in loop, where we make sure that before testing it on a real system, are they working completely fine with the virtual system as well, right? So that is what we do. So in this study, this is the AC microgrid that has been used for this case study. So we have a three-phase connection to the 480 volt grid, and we are connected to the point of common coupling using a circuit breaker. And each circuit breaker is connected to, and this circuit breaker is connected to an AC bus, which contains the elements of the microgrid. And what are these elements? We have a battery, we have a diesel generator. A battery is bidirectional in nature, it can both charge and discharge. Then we have a diesel generator. Then we have load, AC load, which is zero point 0.5 megawatt. And we have a solar farm, which is 0.4 megawatt, right? So what we want to do is we want to check in grid connected mode and in islanding mode what happens in the system. So let's talk about grid connected mode for first. Now, when I say that the AC microgrid is connected to the grid, what I mean is that there is an exchange of power between grid and the microgrid, right? The main grid and the microgrid, right? And if that is the case, then what will happen? So we have to first, sorry, yeah, we have to first talk about how the power flow schemes will look like under both category, right? So in first, we'll consider that since it's in grid connected mode, we'll consider that the grid is supplying power to the load. Grid supplies power to the AC load, right? And now since it is connected to the grid, we assume that we don't assume that, we make sure that whatever the power that we are producing from the PV array, all the power is getting translated to the grid. So what we do, we operate it at maximum power point tracking mode. All right. Now PV operates at MPPT mode. Now what will happen to the battery? So battery is free to either charge or discharge based on whatever um energy management scheme is employed, or let's say if there is need, it can discharge, and if there is no need, it can charge. So battery can either, and it can stay idle as well. Battery can either charge, discharge, or stay idle, right? If let's say it has reached its peak energy storage, it will not charge anymore to prevent it from overcharging, right? And what does diesel generator do? So the diesel generator is used to regulate the voltage if there is any fluctuation. So the diesel generator, the main thing is, so because a PV array is connected, there can be intermittencies, and it the diesel generator just helps in regulating the voltage of the AC microgrid. Right. Now let's say that this is grid connected mode. I mean, it's simply straightforward, right? And what will happen if, let's say, this circuit breaker is open and the AC microgrid now behaves in a in a in an islanded mode of operation, right? Let me change this. All right. So islanded mode, we all know it's just that uh, the microgrid is not connected to the main grid at all, right? Now, if that is the case, we have to empower the load, and we have a PV array as well. We have a battery and we have a diesel generator. So if let's say this has been talked about a lot of time when we were studying about AC microgrid, but let's say that if I want to ask, can PV operate at MPPT? Will it operate at MPPT? Will it always track the maximum power point? Or do we want it to track maximum power point? The answer would be no. Why? Because we know that there are intermittencies, and if when it is tracking the maximum power point, because the maximum power point can change, right? Because if let's say there is a sudden cloud cover and based on the conditions, right? So we don't do that. We make sure that we get a constant output from the PV. So what we do is we derate it, or we operate at off MPPT, right? That's what we do. Now, PV is operating at off MPPT. Now, who will set the voltage of the bus? There is an AC microgrid, and it has a bus at which all of these loads and these generators are connected. Who will regulate that voltage? Will it be battery or will it be diesel generator? It will be diesel generator, and we have talked about it as well, because a diesel generator has both control. We can control voltage and frequency, right? Because we have this uh, we have speed governor control and excitation control, right? So let me just is used to provide control over voltage and frequency, right? And why do we want that is because we can control from because diesel generator has an excitation system and a diesel generator and a speed governor. So diesel generator has a speed governor, and it also has an excitation system. So what does a speed governor, what happened? Okay, someone came and left. Okay, no, all right. So what is a speed governor? So speed governor, what it does is the active power that is inputted to the rotor, we can control it. So if we can control that active power, we can help regulate the speed and frequency of the rotor, right? To the rotor. And how does it do that? I mean, what is the what is the, I should not call it active power. I mean, it's the same thing, but what it does is it essentially controls the mechanical power. Just write mech. I mean, it's the same thing. I mean, if you're controlling mechanical power, you're indirectly controlling torque is directly proportional to active power. It's the same thing. Anyways, we was say yeah. So how does it do that? How does it provide control over the mechanical power input to the rotor, thereby controlling. Just take this space. I'm sorry. Speed and frequency. And what's the formula for that? F, I guess, is equal to Pn by 120, right? Where P is number of poles and N is speed in RPM, right? What essentially diesel generator is essentially nothing but there is a crank and a shaft, right? And the shaft is used to rotate the turbine, rotor of an alternator, a synchronous generator, right? So just like the application is to say synchronous generator, the same things can be applied to a diesel generator, right? Because it's the same thing. We are just controlling how we rotate it, and we have an excitation system. And as we know that the excitation of an alternator, a synchronous generator, is just a DC, sorry, a rotor winding being excited by a DC excitation system. DC excitation system. Sorry, DC is used to. So what we do is where the rotor windings are connected, we just provide a DC current, right? And when we provide a DC current, there is a formation of magnetic field, and since the rotor rotates, it converts into a rotating magnetic field, right? So DC is used to provide excitation to the rotor winding, producing magnetic field. All right, so that is what an excitation system does, right? And by using how much amount of DC current we apply to the rotor winding, we can control the amount of reactive power it produces or absorbs, right? And a simple thumb rule is that when there is when the just a second. Uh, so yeah, so let's say if there is a strong field, that means higher terminal voltage, right? And because the terminal voltage is high, that means there is a more reactive power control, right? So we can use an AVR, an automatic voltage regulator, to sense this terminal voltage in such a way that it maps the original voltage that it needs. So a reference voltage, right? And it maps the reference voltage, and based on the fluctuations, it controls the excitation of the field windings, right? So that is what is the right. So okay. Yeah, so that is what a diesel generator helps in, because we have control over the amount of active power that is input to the diesel generator or the alternator. We can control how much. Just a second. Can you mute yourself, Pawan Reddy? Yeah. you- Okay, I don't know what happened. Okay. So that is what happens with the diesel generator, right? So yeah, and that is why it is used to provide a control over the voltage and frequency of the AC bus at which the microgrid is connected, right? And this is the reason why diesel generator is used for that purpose. And what will happen to the battery? And the battery will either charge or discharge based on what is happening. So we'll discuss how this battery either charges or discharges. So let's so okay, so this is what is essentially how an AC microgrid is used, right? And what we want to do is, let's say that in a grid connected mode and in an islanding mode, the output voltages, current, or anything that is at the point of common coupling, we are sure that the power quality is very high, right? And that THD is low, and that is what essentially we want with our system. The power that we have at the connection point, it should not be distorted. And with any control that we are providing over the controllables, let's say the diesel generator, the lithium ion battery, or any PV array, or even the load. So that is what the case study demonstrates. I mean, I hope that you have all gone through that. I would not be able to do it because that's a video being played over there. But still, what it happens is the as you can see, when it is in grid connected mode, there is a grid current flowing, and this grid current component is purely sinusoidal. But when the AC microgrid switches to an isolated mode of operation or an islanded mode of operation, the grid current is minimal. As you can see, it's negligible, I mean. And what we have is the battery, the PV, and the generator are being used to supply the load that is connected to the microgrid side. Right, and as you can see, the difference between all these between how much the amount of power that we are getting from the grid, and then how much amount of power each generator is, or the battery or the PV is uh, providing to the system. So that is how the instructor dealt with the case study of the simulation of AC microgrid. Moving on, let the second thing that was discussed in this week was the simulation of DC microgrid. So a DC microgrid is simply a microgrid in which we have the main in which we have DC bus, right? And we don't have we don't have to control the frequency of the bus because it's DC, right? And as you can see, all the loads and the even the wind, it's already being produced, I mean, in AC DC, and then we are just using a buck converter to amplify the power from the wind and all of these loads. And we have also a hybrid energy storage system where we have a battery coupled to a supercapacitor. Why we do that, I've went through it a lot of times. It's because battery has a high energy density and low power density. So to make sure that the transients are met, if at all there are in the system, we use supercapacitors, right? And this is how the standalone DC microgrid system looks like. And for that, what we do is we have an energy management scheme. And in an energy management scheme, what we do is we want to make sure that how we are using the system, how we are using the individual generator, the battery, the loads, how we are providing power to them, are being regulated using this management scheme. So we talked about what energy management schemes are. I hope you are familiar. So this energy management scheme is given in this flowchart, and this flowchart is usually read from top to bottom and left to right. So we'll do just that. So what we have here is, first, what we are doing is based on how the uh, grid power is, based on uh, how much power the grid is supplying and how much the load is, we determined what the actions of our S batteries will be, because battery here will provide you the ability to control or to control your DC microgrid in such a way that you are able to provide your load without doing any load shedding. So we'll see. But there will come a time when the load shedding becomes inevitable, and we'll discuss why that happens. So let's start. So what we have is, when we read a flowchart, we have a starting point. It's always given in an ellipsoid or in an ellipse, and any decision which requires which has a yes or no decision, we generally give it in forms of diamonds. So the first decision that we have to see, or the first condition that we have to check, sorry if I'm saying decision, it's condition, or even decision, anything related to a yes or no is modeled in a diamond structure. So the first condition is the grid power sufficient? Is the grid power able to meet the load? Right. Let's say it is able to meet the load. And now what we have is, the load will be supplied by the grid. Now, what will happen to the battery? So what will it do? So the battery, based on the battery's capacity, if it is greater than 90, so we want to make sure that the battery does not overcharge, and that is why we have set a limit of 90 SOC to be at most 90. And if this condition is met, That means that we can't have the PV and wind run at MPPT mode. So what we do, we run the PV at bus regulation mode or off MPPT mode, right? So what they want to do make sure is the amount of power they are producing does not cause a violation of the voltage of the bus, right? And the battery will become idle. I mean, it will not charge or discharge. But let's say it is not at 90 degree. What will happen? The battery is still the battery will be charged, and the PV and wind will operate at maximum power point mode of, right? And what if the condition is not met? If the condition is not met, we will check how the SOC of the battery looks. If the SOC of the battery has not reached 40 yet, that means we can still continue discharging the battery. So we have said that if the grid is available, if the grid is connected to us and the grid is supplying power to us, we make sure that we check how much the battery's SOC is, and if we can charge it or not. So we charge it up to a level of 90 degree. But let's say the grid power is insufficient. Just it becomes insufficient. We make sure the the battery starts discharging and the SOC will drop. And we want to control this drop, and we have set a lower limit of 40%. Okay. So we check if the battery is not at 40%, we still continue discharging and we operate PV and wind in MPPT mode. But if it becomes less than 40 percentage, what we do is we check if we have diesel generator available. So we see there is a diesel generator available, and if the diesel generator is available, we want to make sure that the deficit of the energy, that is load minus the grid, this deficit is the DG producing can the DG produce more than the required amount of power? If yes, we use the rest of the power to charge the battery. And if it is not able to provide that much amount of power, we move to condition D. So you have two conditions to check. When the DG is not available, we go to A, and if the DG is available but it is not able to meet the deficit, and we move to D. Let's check for A, right? And just in case, so whatever we are doing here, we move to C, and C is nothing but we reach back again at the starting point, right? Because it's an iterative procedure, the microgrid continues operation. We don't have a control. It's not an episodic task, right? We don't have a termination task or a terminal state. It continues, and it continues its operation um, as much as possible, right? So first we check if the DG, when the DG is not available, what will happen? So we move to A. In A, we check if the battery's SOC is less than 40 or not. So we came to this, and the battery's SOC was less than 40. And we want to, and if the battery's SOC is not at 40, let's say, and we are at this position, we continue discharging the battery, but we make sure we shed some load, right? So we make sure the load is shed in such a way that we have all the critical loads, right, being met. Let's say that we have, this is a critical load, and this is a non-critical load, right? So what we do, if the battery's SOC is still greater than 40%, we continue its discharging, and we make sure all the critical and non-critical loads, here it's not being shed because the SOC is still greater than 40%. But if battery's SOC is less than 40%, we move to a separate decision where we want to check if the SOC has reached 30% or not. If it has not reached 30%, if it is between 30 to 40%, right? If it is between 30 to 40%, we shed one non-critical load and we continue supplying the critical load as well as one non-critical load. But as soon as the battery's SOC becomes less than 40, less than 30, what we do is we continue discharging, but we drop all the non-critical loads, right? So as I've told you, critical loads are something that you have to make sure that you are able to provide power to these loads, such as a critical load is nothing but your hospital loads, right? These are critical loads. You want to make sure that they have power at all times. So how we do that is by checking how the batteries associate, what is the level of the batteries associate. Now that is when there is no DG available. But let's say there is DG available, but the DG's power is not sufficient to meet the deficit. That is the deficit created by PL minus PG. So we move to this. So we check if the battery's SOC is less than 30. So we have some power coming from the DG, right? There is some power, but not the whole amount of power. So we can make sure that we can discharge the battery further down. I mean, earlier we were just discharging it to 40%, but we can now ensure that it can discharge up to 30%, right? We check if the battery's SOC is less than 30%. If it is not less than 30%, we meet the whole load. We supply all the critical load as well as the non-critical load. As soon as the battery's SOC goes below 30%, we check if it is below less than 20% or not. So this is 20 to 30 and this is less than 20, right? If it is between 20 to 30, we shed one non-critical load and we supply power to a critical and a non-critical load. So we have two non-critical loads and we choose to supply power to one non-critical load. As soon as the battery's SOC becomes less than 20, we shed all the non-critical load and we provide power only to the critical loads. So, and the cycle continues. So we continue checking the flow chart because it's an energy management scheme, right? And that is the benefit of using this scheme, because we can make sure that how how well we use our resources. So let me write somewhere. So just write it. I mean, I'll write it here. So the EMS helps us. One. So how is the EMS helping us? It helps us in keeping the battery within the safe limits, right? Right. The second thing that we want to do is we want to make sure that priority loads or the critical loads are supplied and are protected by the. Okay, so we want to make sure that the priority loads or the critical loads are being met at all times, and we don't want to, and we can have a procedure to shed non-critical loads if we have to, right? Right. So we have a schedule to check when and how the non-critical loads are scheduled. And that is what an EMS does. And we have discussed this a lot of time in our lectures before. And I hope you remember all of that. Next case study that the instructor, and I'm not going to through the demonstration. I mean, there were videos and there were this uh, I mean, the instructors have discussed about that how they have done the demonstration. So I would appreciate if you have watched the videos, because I can't cover that. I don't have experience with what the kind of system they were using, but still I will try to convey you everything that there is to learn about these two things, right? Next case study they performed was to interconnect the two local DC grids, right? So what benefit do they provide? So a DC microgrid in itself, what it does is it is able to. Hmm. So in itself, it's able to use the distributed energy resources and the storage elements to provide power to the loads while being connected to the grid or not, right? But when we have two DC microgrids in close proximity, we can have an interconnection, and that happens. We in itself we have being the Indian power system is is divided into separate control areas, where two control areas are connected to each other using tie lines. And the similar concept comes to DC microgrid as well, where we use a bidirectional converter to interconnect the two DC microgrids. So what advantages do they have? So one, interconnection makes the overall system robust and resilient, right? So since you have in two interconnected DC microgrids, you know that you will never be out of uh, generation, right? If you need. Why? Because if let's say some DC microgrid which you are interconnected with has surplus generation, you can always transport that amount of power to your DC microgrid, and that is how you can make sure that any outages that you suffer um, can be met by having generation from the other microgrid being available at your site, right? And that is how you make sure that your system becomes more robust and resilient. Second, you can increase your efficiency. So let's say you have loads at your particular, let's say at a very remote area, and you have some distributed energy resources which can provide power, but not the whole power at all times, right? They cannot provide the peak demand. So what you can do is, and because they are very remote, you have to make sure that, and you know that there is some other place where the load is less, but the generation can be huge. So you can connect these two remote areas in such a way that you can make sure that the power can be transported to this area where the load is more, and the surplus generation can be used over here. So what happens is the efficiency is increased. You are able to balance supply and more supply and more demand, right? And that is how the efficiency of the system increases, because you are increasing the management of the loads. Because the peak demand is more, you require more power, and how you can have more power is by being connected to a separate DC microgrid which can have surplus generation, right? Third, because this happens, you can have power sharing and trading, right? So when you are connected to a DC microgrid, you can trade power, right? You can be like, okay, how much power do you want? If it has surplus generation, it will be able to sell it, right? And it will be able to make money. And by putting a price on it, you make sure that nobody is nobody is underpaid, right? Because you are putting power a price to the power, and you will not put a less amount of price, right? Why will you want to sell it at less than what you are generating it at, right? And this will help us in doing what? Integrating more renewable energy resources. And these are some advantages of the how interconnection will help in managing two isolated DC microgrids, right? Okay, and I told you, right, they require a bidirectional DC converter, right? And this bidirectional DC converter is shown over here. It's a dual active bridge converter, DAP converter. It's an H bridge configuration, and you see you have this transformer, right? This is a high frequency power transformer, and what it does is it helps in, just a second. So while acting as, a step up transformer or a step down transformer whenever you want it to act like, it can also provide isolation. What I mean by isolation is that, let's say there is any fault occurring on the right hand side of the system, right? In the DC microgrid too. that fault can get transferred to the DC microgrid 1 if it is just simply connected with no isolation. But because there is an isolation in the form that, how does this isolation comes? Because the transformer are not interlinked. The windings are not weaved together, but they are interweaved in a sense that they are just magnetically connected. They are magnetically coupled, and because they are magnetically coupled, the fault cannot transfer between these two magnetically coupled wires, and that is why you provide isolation, and that is very much required. You want your resources to be isolated as much as possible so that any fault that the grid have or your may have, that will not transfer into the grid or vice versa, right? So that is what the usage of this tap converter here is. And the control is fairly very simple. It is divided into separate zones, and you have two regions. So in region, based on the voltages at V1 bus and V2 bus, the control over, here they have represented it as VA and VB, but it's essentially just V1 bus and V2 bus. Based on the voltages, if the voltage is higher and it's not same. I mean, when it's not same, if one voltage is higher than the other, the power is transmitted from the higher voltage level to the lower voltage level, right? That is something that we all know, and that is how the configuration here is provided based on the kind of zone they are, based on the kind of region they are. Given the one which is at a higher terminal voltage level, that supplies power to the lower voltage terminal level, right? And that is what is provided here. And this is pretty self-explanatory. I won't go into details. If you have any doubts, please use the chat box since you are not present here at all, right? Anyways, okay, just a second. Hmm. So next thing that the instructor discussed was simulation of an AC-DC hybrid microgrid. So let's say you have a hybrid microgrid, which is, it has both AC components as well as DC components, right? And how do you manage to control it? So I remember telling you that for this as well, you have schemes, energy schemes, but one particular type of energy scheme is coordinated voltage control schemes. So what you want to do is you want to make sure that the voltage is always regulated, and for that the scheme used is called as coordinated voltage control scheme, and that is what we will go through today. But first let's discuss what the system in study is, right? Okay, yeah, sorry. So what you have here is you have a 33 IEEE 33 bus system. So you have an IEEE, right? You use an optimization technique to figure out at which bus you should connect your AC microgrid or DC microgrid. I won't go into to that details, but based on that, the instructor has connected the DC microgrid at bus number 5, and the AC microgrid is connected to the bus number 22, right? And what we have here is the DC microgrid has batteries, PV, and DC loads, while the AC microgrid has a D statcom, very good, and a DFIG and some AC load. So what is a D statcom? So D statcom is used to regulate the voltage. It is called a static compensator. It is used to to regulate the voltage of a particular bus, and that is what it is used for by using exchange of reactive power, right? And we also have one more thing over here, and it's called an OLTC. OLTC is called either an on-load tap changer. So I'll remove this. We all know it is called IEEE 133 bus system. Okay, we have it's called on-load tap changer or online tap changer. Anything is fine, right? What it does is based on it has the number of steps. It's right now it's 16 steps, and so what it does is it produces 1 by 16 variation, which is 0.1 per unit. So what it does is, based on the number of steps, it is used to regulate the voltage between 0.9 per unit to 1.1 per unit. right? This is called a 10% band of voltage. So voltage should always be between 0.9 and 1.1. And the OLTC produces a change of 0.1 per unit for every step that it takes, and there are a total of 16 steps. So the total change that it can provide is, just a second, 0.00 or 0.0. Yeah, it is 0.00625 per unit, right? With each step, it can provide a change of 0.0625 per unit. So this is, and it is used to regulate the voltage. Same way D-STATCOM is used to regulate the voltage. We can have DFIG, the converters connected to the DFIG can also be used to provide control over voltage. We have this AC-DC inverter. No, sorry, it's not an AC-DC converter, it's a rectifier. And it is also used to provide control over voltage by controlling the converters, both this as well as this. Right, so there can be many things that we can do. And what we want to do is we want to make sure we operate all of these devices, the D-STATCOM, the converters, the OLTC in such a way that they can, without communication, self-sustain the voltage at all buses. They can make sure that the voltage never goes beyond the permissible limit, right? And that is what the usage of the coordinated voltage control scheme is. So let's write about it. So it's called a CVC scheme, right? Coordinated voltage control scheme. So what it does is we want to make sure that the voltage levels across the AC/DC microgrid stay within the operating limit. So what we want to do is maintaining very good, right? So you want to make sure that they stay within this permissible band, and right. And how do we do that? We do that by providing control over the different devices that we have. So how? Right? We want to, right? Very. And how they do it is by through exchange of reactive power. Right? We all know reactive power produces change over voltage. Right? So these schemes are of two types. It's either centralized, so we can have a centralized scheme, or we can have a decentralized scheme. So in centralized, what we do is there is a central operator which controls each device based on global variables. So it requires communication. And in decentralized, we can control each device based on the local variables that they are witnessing. So it is called no, it requires no communication. And as you can see, we have mentioned in the figure as well, VM1, VM22, this VM5, all what they are trying to do is control their respective bus voltages so that the total voltage across the AC/DC microgrid stays within the level by just controlling over the corresponding buses. That's why this scheme that the instructor has proposed yeah, um, is a no communication scheme. It does not require communication. It's a decentralized scheme. Now, what used to happen is this is the kind of CVC that existed before. So these are three different states that it used to operate with. So in the first state, the required reactive power was less than 40%. And we used to check, okay, if the voltage is between is greater than 0.9% or not. If let's say there comes a time when the voltage is greater than 0.9, it is greater than 0.9. So you see VM is greater than 0.9 per unit. So that means it's in safe level, but the Q requirement in the system has increased. So Q required has become greater than 40%. Since the requirement has increased, if we increase it, if we increase reactor power as well, because the requirement has increased, what will happen? The voltage will inflate, it will increase further, right? So what we do is we hard limit the Q across all devices to 40%. So that means you won't get more than 40%, that's for sure. So that this is called a dynamic state. Mostly you will find your system between dynamic state only, right? And let's say when you are at dynamic state, the voltage starts dropping and it becomes less than 0.9. You move to a different state, which is called a transient state, where you want to make sure all the reactive power that you have in the system is input. And we increase this hard, we don't have this hard limit anymore. We increase the limit and we increase to 100%. And we make sure that the voltage can bounce back between the greater than 0.9. If VM becomes greater than 0.9 and Q required becomes less than 0.4, we move back to state 1. Or if VM is greater than 0.9 but Q required is greater than 40%, since the VM is already at a safe level, we hard limit the Q to 100% to 40%. So this is how the states behave. So between this transients, what we do is we just make sure how much amount of active power we are having in the system and the kind of we need, right? Active power we need. And how does it happen? The in steady state, we usually don't witness much, but we have switching off small loads, right? This can make the system. This won't have any effect on the system, right? So switching off small loads, it won't have many effect and the state will stay at steady state only. But in dynamic state, what happens is there is a large load switching. But even though there is a large load switching, what happens is the voltage is still in feasible region. We don't want to do any kind of reactive power injection, or we don't want to take any reactive power injection back from the system. But in transient state, there is some fault has happened. Aggravated by switching off loads. And for this, we want to make sure all the devices that we have in the system are able to have the limit of up to 100%. They can inject up to the 100% rated capacity, right? And this is what the CVC scheme. So this is an existing CVC scheme. So this is what existing CVC schemes do. Right. So these are existing CVC schemes, but they have one caveat, and that caveat is in the form of slow acting and fast acting devices. So there are either slow acting devices, which are OLTC. So they have mechanical movements, right? So these are generally called as slow acting. Just a second. Right. So these are called as slow acting devices. So and the converters and these statcoms, these are all fast acting devices. So what happens is they may happen that fast acting devices may be called for injecting reactive power along with slow acting devices, which can lead to a domino effect, right? If that can have so let's say you have this and you switch on all compensating devices, right? For slow acting devices, which are represented green, slow acting, and we have orange, fast acting. When you do that, the fast acting devices will turn on immediately, right? And but it may so happen, sorry, the slow acting ones, they turn on like this, right? Now what will happen? There will come a time, it may happen, I don't know if it will happen at all times, but it may happen that the reactive power becomes more than what was required, and that will further cause a devastating effect to your system. So we need to make sure that the existing CVC schemes can, see how much delay the slow acting devices will produce. But at the end of the day, slow acting devices are the most reliable devices because they will ensure that there is at least 0.0625 per unit of increase in your voltage level, right? So that is what the instructor discusses over here. So let's go through it once. Right. So I've magnified it. I don't know how much it is visible, but I hope it's enough for people to see. I don't know if it is being recorded. I hope this is being recorded. Anyways, right. So what you have is you have this system. I never knew, you could have this whole thing in full screen. I just saw it today and I was so happy because all of my videos were very, these were not much visible. So I was very, I used to be very sad, but I don't know if it's visible in recording. We have to see. I mean, I don't know. The recording is still going on. I mean, I hope it is visible. Anyways, so let's move on. So so this part of the scheme is existing one, and this part of the scheme is the proposed one, right? So two things that we saw here were reaction time of slow. I should write it like cons, and then it'll be much better if someone just goes through the notes. What will you see? Taken into account. Very good. So let's talk about the existing scheme. So what we do, we check the voltage level at the magnitude of the voltage level at all the buses at which the compensating devices are connected to. Right. Again, this is the flowchart. The steady state or dynamic state of the system is represented in this blue box, and the transient state is represented in the red box, right? So let's talk about this. So if let's say the VM is beyond the stable operating limit or zone, right? So what will happen? In this case, because it's a transient state, we want to make sure that the uh, the OLTC, if let's say that its steps are exhausted. I mean, it has 16 steps and all the 16 steps are used, and still the voltage is not in between 0.9 and 1.1. It stops, and and in the and the DC microgrid, we isolate it. Why do we want it to be isolated? It's because we don't want the lack of this voltage becoming very less to be transported to the grid side, right? So both OLTC and DC microgrid shift to a slave mode of operation. In slave mode of operation, what we do is uh, they don't produce a change on their own. There is a master which controls if it wants to produce a change or not. What we do is we make sure that the dstat and the grid side converter, so what WGSC here is this. I think it's a wind grid side converter. I don't know. So what you do is you make sure that they behave as a master in operation, and what you do is you set their reference to 100%. So you want all of the reactive power that they can generate up to their maximum rated capacity to be generated. And you check, you go back to see and you check if the VM is still less than 0 0.9 or not. And since it's isolated and you are supplying all the amount of electric reactive power you can from the converter side, it may so happen that it starts coming back to its stable mode of operation. Once it does, what you check is now you make your OLTC behave in a uh, in a master. Uh, the OLTC becomes the master of the operation, right? And since OLTC is the master of the operation, what it does is it will increase or decrease taps accordingly the kind of variation it is witnessing, right? Based on that, it checks if the VM is between 1 per unit, it's at 1 per unit or not. If it is not at 1 per unit, as I told you, it just hard limits the queue if what it checks if the queue required is less than 40%. If it is less than 40%, that means it's a steady state. Your dstat, your DC microgrid, your wind grid size converter, all of them operate in a slave mode of operation and supply queue accordingly, right? Oh, sorry, my bad. Because it's a steady state, you want them to operate as a master because they can control how much amount of reactive power they can contribute to. So they supply Q accordingly because the Q required is less than 40%. But let's say the Q required is not less than 40%, but it is in a steady state. So it now behaves in a slave mode of operation. That is, they don't have a brain of their own. They follow the commands that are given, and the command that is given is that Q should be hard limited to 40%, and that is what they did. And this is what we have been doing here in this existing CVC scheme. It's being just transported over here, right? Hmm. In your proposed scheme, the transient system behaves the same way. I mean, you control it by having the OLTC in the slave mode of operation, the DC microgrid converted at the isolated mode of operation, and the DStat and WGSC, they are set at 100% so that they can supply all the reactive power up to their rated capacity, right? But what you do here is you just produce a time delay. Just a second. So what this time delay is, because OLTC first behaves in a master mode of operation, sorry, it will control, it can increase or decrease its taps. So if it does, you have to check if certain time has passed and that has been issued, that command of the increase or decrease of the tap has been issued. If the delay period has not passed, you don't do anything. Your DC microgrid converter's reference of the reactive power is set at 0. Similarly, your DStat or WGSC converter um reference reactive power is set at 0. But let's say the delay period has passed, you check if the VM is 1 per unit. If it is 1 per unit, you can still have them at a 0 reference because you don't need to do anything. They are at perfectly balanced conditions, right? VM is 1, that is what you want. But let's say they are not, you now calculate the amount of reactive power you are consuming. So you see, earlier, what you were doing, you were just hard limiting it to 40%, right? So they didn't have an intelligence of their own, right? So I should also write, mm, can I write 2 here somewhere? No control over reactive power of, no dynamic control I should write. right? So, but here what you're doing is you are calculating the amount of reactor power that is required for the DC microgrid converter only, right? And here you can check what they do is they check what is, so it's simply under root of S square minus P grid square, right? And you check the amount of reactive power the grid could supply. So QG will be nothing but under root of S square minus PG square. And that is what they do. And they set the reference at this value. Right. Similarly, but for the other two converters, the D stat and the WGSC, what you do is you just hard limit them to 40%. Right. So you are, so dynamic control over compensating devices, I should write over DC microgrid converter. That is much better, right? So what you're doing is you are presenting them with a mind of their own, right? They are able to provide what is called as uh, they are able to provide both time delay, so as to check if the amount of reactive power that has been supplied from the OLTC, if all of that has been consumed or not, and then they supply whatever is available at the grid side based on the kind of converters rated capacity is, right? So this is what their proposed scheme does, and it is able to meet the challenges. So challenges of the earlier scheme. So let's discuss what the earlier scheme was and the disadvantages and the advantages are, right? So the disadvantages were simply, so what was the first time? So the speed of the speed of the operations of the devices were not taken. Speed of operation of devices was not considered, right? And speed was not considered, and then availability was also not considered. Availability, right? These were the three things. uh okay, this is all. Advantages, if we want to check, so what we have done is we can we have improved the efficiency of the utilization of the devices, utilization effectively increased. Second, what we have is we improvement of the fault right through FRT, fault right through capability of the, right. So I mean, you can check, I mean, the slides for more, but I will just leave it here. Right, so that is what you do. You check what the operating state is, and then you check if the delay has been. So what is the time delay? This has been taken from the first slide. So time delay, I'll just check if hmm, it's 1 minus V bus into TOLTC upon VOLTC. So this is the time delay that you have to check for your slow acting devices. Right. Then moving on, the next thing that the instructor discussed was parallel operation of inverters. So why do we want to have parallel operation of inverters? It is similar thing, right? We have parallel operation of synchronous generators or DC motors, right? And the same thing is applied over here. What it necessarily does is we can increase the capacity of generation, I mean generation capacity of a device, right? Because we have parallel inverters which can increase the amount of power that you can extract, right? And so what it does is So it increases the generation capacity of the inverters. Inverters connected to DRs. Right. What else do they do? Hmm, all of these inverters act as parallelly connected current sources. Right. So this is what the thing is. Hmm. So what we do is, let's say this is the inverter. What we do is we have an LCL filter to filter out high oscillation frequencies, and we parallelly connect them to a point of common coupling, which is then connected to the grid, and all of them behave as a as a current source, right? Because they produce I21, and since they are directly connected across uh, an inductor, they behave as a current sources. They behave as current sources, right? Now, why do we want to ensure parallel operation? So there are a few things that why we have to write why. One thing we know is that they increase the I mean uh, they increase the generation capacity of the RES, they are DRs that they are connected with, right? I had one more issue to discuss with, I forgot. Hmm. So we'll come back to this. Okay, one is increasing, right? The second thing that we want to make sure is that efficiency is improved. So let's say you could have gotten more power out of a solar power plant with multiple inverters connected to it, but you have just a single inverter connected, right? So since you are extracting more, you are indirectly or directly increasing the efficiency of the system too, right? So that is why they are important. And how do they do it? So there are some challenges. How do they do it is simply, right? You use an LCL filter to filter out the high oscillating frequencies, and you just simply connect all of them to a simple point of common coupling. But there are some challenges in their operation, right? And what these challenges are, they give rise to interactive currents and common current, right? So there are two kinds of current: interactive current. So these currents are circulating currents flowing between inverters, right? Then there is a common current. The actual current input to a grid, right? So the common currents are the one that are getting transported to the grid. These circulating current, these flow between the inverters. And how do these flow between the inverters? They can be same magnitude, but so they are of same magnitude, but they are out of phase to each other. Right. So what they do is these flow between the inverters. And how do they flow? Let's say there is an inverter one connected here, and this V1 and this terminal voltage V1 is greater than V2. Now if V1 is greater than V2, I've already told you what will happen is the current from the higher voltage side will transport to the lower voltage side, and there will be a circulating current. This won't go to the to your grid, but this will cause unnecessary heating of your inverters, right? So these are something that contribute to losses, and you want to make sure that the losses are minimal and that whatever you're producing is being transported to the um, grid, right? And they are of high frequency oscillation, so they basically have a high frequency oscillations, and you want to make sure that they are you want to make sure that their presence does not make the system unstable. And now how do you do that, right? So let's talk about that. So let's see, this a single inverter along with their control system. So let's call this C. This is control, and this P. This means controller block, and this is plant block, right? Now let's say that if I want to get a closed loop transfer function, closed loop gain of the whole system. So the closed loop gain of the whole system, G1 is nothing but I21 by I ref 1. So what is the closed loop gain? What we are getting at the output, which is I21, and what we are giving at the input, which is I ref 1. Right? Now, how do we get this G1? So this G1 is nothing but G0 upon 1 plus G0, where G0 is open loop gain or open loop or forward path transfer function. And this open loop gain is given by P times C, right? Whatever this plant block is and whatever the C block is, right? So let's talk about C block. So C block is what we are giving as input is error term, and what we are getting output is V naught 1. So what we have is V naught 1 upon E, right? Hmm. That is what we have, and what we have at the P side, which is I21, and what we are giving at input is V naught 1. So what we have is I21 upon V naught 1. And then the closed loop transfer function becomes, what is G naught? G naught is simply I21 upon E. So if we write, it becomes I21 upon E plus I21. Now what is E? E is nothing but I ref 1 minus I21, right? So equate this in this. So G1 now becomes I21 upon I ref 1. So that is what we have written over here. So this is how the closed loop transfer function is formulated using the open loop function. Right, so we got the closed loop transfer function. Now, why we have gotten this is because we want to check if the system is stable or unstable with the presence of the circulating currents, which are interactive currents, right? And how we do that is through checking the gain of the system, right? We check poles and zeros, right? And I hope you're all comfortable with control systems and how they're modeled. So let's see. Now I won't do the whole demonstration here. I mean, it's a very lengthy derivation, so I'm just doing a part of it, just like Sir has done. If you want to, get an in-depth analysis of it, the references that he has cited will be of a very good use to you. And I won't go into that. It's unnecessary for me. Right. Now, let's say that you have two parallel inverters connected to each other. Now, in this two parallel converters, what we have is we can write their output in terms of their transfer function and input variables as this G11, G12, G21, G22, and what we have is V, no, not V naught, we have, yeah, V naught, V naught 1 and V naught 2, right? So what we have is we have an open loop function. That is what these are open loop transfer function of plant, right? Now what you do is you let the inverters be identical. I mean, I will do it later, but how do you get this? I mean, how do you, let's say I write one, I21 is equals to G11 V naught 1 plus G12 V naught 2. Now you'll say, how do you find these G11, G12? It's simply by using superposition. How do you use superposition? You short circuit one voltage source. That is what is done over here. You just keep V naught 1 as active and you find out what is the uh, value of V naught 1 upon I21 using this whole system. Similarly, you short V naught 1 and then keep V naught 2 and just check what is the transfer function of this diagram, and you can effectively get all of these values G11, G12 and G21 and G22, and you will see that G11 and G22 are same and G21 and G12 are same, right? And how they are given is for a 2 bus system they will be given as GP by 2 plus GC by 2, right? And for this G12 they will be given as minus GP by 2 and plus GC by 2, where GP transfer function without LG, you don't take grid into account, and in GC you obtain transfer function with LG, you take LG into account here, right? So you do this, and for an n bus for an n parallel connected system it will look something like this. G11 is equals to G22, which is n minus 1 upon n GP plus GC by n, and you have G12 equals to G21, which is minus 1 upon n GP plus GC by n, right? That is how you write it. And if I want to get GP and GC, so GP and GC, I'll just take these values at how they were given in instructor's slides. So this is 1 upon S L11, L21 C11, and you have 1 upon S square plus omega square. Similarly, GC, since you are taking into account your LG as well. So what it is SL11 L21 plus NLG times C11 1 upon S square plus omega R square, right? And you have, let's call it, uh, yeah, let's call it omega square and this omega R square, right? So omega is your resonant frequency, and this resonant frequency is given by L11 plus L21 by L11 L21C, and omega R is your resonant frequency when you consider grid 2, which is L11 plus L21 plus NLG upon L11 L21 plus NLG times C. Hmm. Right? Okay, so that is what you have over here. So these are your frequencies. Now, if you want to check all of your, the transfer function, based on these transfer function, you can calculate your interactive current component and your common current component. Your interactive current component will, bear with me. I mean, if you are not understanding, it's totally fine. You don't have to get everything at once. Pause the lecture, go to the references and the reference papers, go through the instructor slide once more. You will be able to catch this. So what is this? 1 upon n GP times D upon GP plus, sorry, GP D plus 1, and this is I ref 1 minus I ref 2 for a two parallel connected inverter. So this will be half minus I ref 2, and I common will be 1 upon 2 GCD because it's going to the grid side. GCD plus 1 I ref 1, it will be algebraic sum because you are taking both of them into account. And D is nothing but transfer function of, so I won't write D, I will write C because it's transfer function to voltage which we have taken as C controller block, right? G S C C, right? C is nothing but V naught 1 by, or output voltage by error function, transfer function. Right, now what you want to do is you want to check if the poles of this characteristic equation of I int is where, like what is the contribution of the poles of this. So what is the poles? You get 1 by GPC equals to 0, right? And you check what is the value of what the S, this GP and C are a function of S, right? S, and you check what is the value of S poles, right? Once you get that, once you get those, you then plot them and you see this is the S plane, right? If they lie here, the system is stable. If they lie here, the system is unstable. And if they lie here, the system is marginally stable, right? That is how you get the, this is the real axis, this is the imaginary axis, right? And that is how you get the, if your system is going to be stable or not, right? Next thing that so I know this is a bit too much for you right now, but try going through the papers once. Try doing the derivation again. I've done one derivation for you here. I've shown you the way to derive this derivation. The next you can do on your own, and I'm sure you'll be able to get. Next, the instructor wanted to discuss was of the effects of the harmonics. So what are harmonics? Harmonics are your unwanted noise in the system. So that deviates the waveform from being pure sinusoidal to a different waveform, right? From not from that makes it not behave like a pure sinusoidal waveform. So what I mean by that is the fundamental component is always the first harmonic, and as you can see, it is a purely sinusoidal waveform, right? So let's say the frequency was 50 hertz. If frequency is 50 hertz, the frequency here is 50 hertz, right? The second harmonic component is nothing but, harmonics are what, F into N times your F naught. Let's call them Fn. So Fn becomes 2 times 50, which is equal to 100. So these are fast oscillating uh, harmonics, right? So these are high frequency oscillation. So as you can see, this is there, and let's say there is the original component also present, the 50 hertz component. So what they do is they distort the waveform. As you can see, instead of the waveform behaving like a pure sinusoidal, it now behaves like this, right? So the output waveform is now distorted. Similarly, the third harmonic is nothing but your 150 hertz, and you see the waveform is distorted even more, and this continues, the cycle continues. Now the frequencies, the fundamental frequencies and the harmonics are also divided into their type of sequence that they follow, rotation sequence, right? If the rotation sequence is normal, it's ABC, it's plus, or if ACB, right, I'll write it here, ABC, ACB, or no rotation, right? So the fundamental component rotates ABC and they rotate at 50 hertz. Then each component gets multiplied with the harmonic value, which is second behaves as a negative sequence harmonic, and the third or the triplet harmonics behave as zero sequence harmonics. Now the positive sequence harmonics, they cause heating effect in your system because they rotate at the same direction, and since they are rotating at the same direction and you have a positive sequence harmonic present in the system, they also cause the rotor to rotate in this continue rotating in the same direction, which now causes a heating effect in the rotor. But let's say if the sequence is reversed, that means the sequence now becomes a negative sequence. So that means the rotation is reversed, and if the rotation is reversed, it causes torque problems in your motors. And if there are triplet harmonics, which are of the form 3 times n, what they do is they have no rotation and they just cause the neutral wire to have currents or voltages, and they can cause heating as well. Right, so this is what harmonics is, and what power quality is. So if I want to talk about power quality is the health of the power you're getting, right? So the presence of harmonics causes distortion in the power quality. The harmonic distortion then degrades the quality of the power that you're getting from the sources, right? So what you want is you want the waveform to behave ideally as sinusoidal as possible, but their presence makes them non-sinusoidal in nature. Now, how do these harmonics come into play? It's because of the presence of nonlinear loads, right? So what are nonlinear loads? So nonlinear loads are those loads that don't follow Ohm's law, which says that V is proportional to I, right? So increase in current directly increases the voltage, right? And what are their examples? These are your power electronic devices, your diodes, your what is it? Diodes, and what do you have as, right, switches. So these are all your non-linear loads. And so why am I saying they are non-linear? Let me just draw the graph. Right. Ideally, these are linear loads like resistance. Voltage varies proportional to the current. But non-linear loads, what they do is they behave like this. And they have like this, right? This is a diode VI characteristic. So now you can come and say, okay, diodes and all these power electronic converters, what they do is they they distort, they produce harmonic distortions, they have harmonics, but still we use them, right? Why do we still use them? So it's just because the benefits outweigh their cons. So they provide a lot of benefits, right? They make the system less bulky, and you have by just controlling the amount of switches, you can convert the waveform from AC domain to DC domain, or DC to DC, you increase the the power that you're getting as well. So you see the benefits outweigh, and that is why you then propose newer solutions, right? And for this you have power quality mitigation techniques, and for these you have passive filters, which are just LC combination. So you can have either shunt, series, and hybrid. So these are your shunt uh, uh, these are your shunt filters. What they do is they are connected across your devices between ground and your bus, and your series are connected with the devices. So you see, so you have these passive filters. So they have their pros. If I want to write, let me just increase. So what their pros are: one, they don't have any initial cost, right? They are very easy to make. Low initial cost, low maintenance, simple design, right? You know, it's a simple design, right? But there are cons as well. So let me just demark it. So you have cons. And what are these cons? So you have, because you're using LC components, they can make your system bulky. So these are bulkier, right? And because you are using them, because you fix the inverter, inductor side, capacitor size or resistance size, the filter characteristics are fixed. They are not dynamic. You can't control them on the move. So not adaptable. Very good. Then you have active filters. So as I told you, they are not dynamic in nature, right? So you use active filters. So what they do is you have an active power filter which uses PE devices again. So you are using PE devices to, you know, provide control over your power quality as well, right? So this is what they do, and they have pros. So one major pro, as I've already told you, they have dynamic characteristics. So these are dynamic. Next, so uh, because they are shunt type, they are better suited for current quality, right? But they have few cons as well, right? One is because you have these converters and all, there is a high upfront cost, right? You require, and then you have complex design. Since you design converters and all, the design becomes complex in nature. Then you have series active filters. So these series active filter, because you have, these are suitable for your voltage quality issues. And what you have is again a series connected device where you use, instead of directly being connected across your nonlinear node, you use a sort of, you know, a voltage enhancer or a transformer and then connect your filter across it. So the pros are suitable for voltage quality. Second, dynamic filtering. Again, you have dynamic filtering here as well. But again, there are cons, high upfront cost, complex design, right? Then you have another kind of converters which use both um, series and shunt types of compensation. These are called unified power control quality conditioner. Unified power quality conditioner, right? And because they have both series and, so they will have pros, suitable for both, right? Uh, what are there? Hmm, I think it's, and cons, they have highly complex design, right? They have a highly complex design and highest initial cost because you're using both, right? So these are some things that were discussed, and they also show the application of UPQC to to show how the compensation affects the power quality. And you can see that the power quality earlier was very distorted. The waveforms were very distorted, but after using the compensation devices, your power quality was highly improved. Why do you want this compensation? Is because industry has set a standard. The industry has mandated that the THD of whatever you're proposing should be less than 5%. What is THD? THD is called total harmonic distortion, which is measured as THD is equal to under root of summation n equals to 2 to infinity xn upon x1. So how much the contribution is from the harmonics compared to the fundamental component, right? So this is all I wanted to discuss today. So we started with the demonstration of AC microgrid. We talked about how the isolated mode of operation and grid connected mode of operation happens. Then we discussed DC microgrids, their energy management schemes. Then we discussed about interconnecting two local DC microgrids. Then how it happens. Then we talked about AC-DC microgrid in depth. What are coordinated voltage control schemes? How does the instructor, which proposed a case study, improve the existing scheme? And then we discussed about parallel operation of inverters. We discussed how by comparing the poles of the transfer function of the um, the circulating current or interactive current, we can get if the system will behave stable or not. Then we checked what are harmonics and how the power quality mitigation techniques are developed, and then we discussed a case study as well, right? So I hope you will go through all of this lecture again, and if there are any doubts, you can always come back and ask me in the comment section, right? Let's talk about the question. Since no one in is there, I will just assume that you all know. Dash transformation converts ABC to DQ not reference frame. So I've already told you there are two kinds of reference frame conversions. There's ABC DQ0 or there is ABC alpha beta 0. So the DQ0 is called Parkes transformation and alpha beta 0 is called Clark's transformation. So the correct answer is Park for 1. Then next, identify the correct statement. An under-excited synchronous generator injects reactive power into the system. False. An under-excited will always take in, absorb power because it is under-excited. An over-excited system injects. This is correct. And normally excited operates at a leading power factor. Wrong. Normal operating will not operate at a leading power factor. So the correct answer is B. Identify the correct statement. The battery and capacitor are connected to an isolated DC microwave through a unidirectional buck boost converter. No, because you want both charge and discharge of power, right? So you want to make sure that they are bidirectional in nature. So the battery is connected to an isolated DC microwave through bidirectional boost converter, correct, but not a supercapacitor. No, supercapacitor is also it also needs to charge, right? So the battery and are both connected to a. So the correct answer is C. This is also wrong. Fourth, which one is a voltage regulating device? OLTC, DStatCom. Both are voltage regulating device, right? Both are able to produce an effect in the voltage by using them. Fifth, an OLTC is connected between nodes 1 and 2, the regulating voltage at node 2. So we need to regulate voltage at node 2. And with respect to node 1, the voltage at node 1 is 1 per unit and the tap position is -10. Okay, so we are stepping down and V2 is nothing but, since we are stepping down, we are converting V1 minus VOLTC. And V1 we know is 10. Oh, sorry, 1. And OLTC is connected to -10. So we'll just add plus and this will be plus -10 times 0.00625, which becomes 1 minus 0.0625, which becomes 0.9375. So the correct answer is B, right? By taking into account how much effect the OLTC will produce per step, we can get this value. So the correct answer is 5. In steady state operation of the transmission grid, the voltage magnitudes are regulated in the range of 0.91 to, no, this is wrong, 0.95 to 1 point, this is also wrong, this is also wrong, this is correct. In distribution side, we have 0.95 to 1.05, but not at the transmission side. Seventh, multi-parallel inverter system connected to the grid acts as voltage source is wrong, current source is correct. Power source is wrong. So the correct answer is current sources, because they are directly connected across an LCL filter, and because there is a presence of inductor, it will make sure that the current is always constant. So that is why they act as current source inverters. 8. Select the current statement in the context of multi-parallel inverters. Common and interactive currents will be unstable if the poles of the characteristic equation lie in the right half of the S plane. So if we check if the poles lie in the right hand, right, we have unstable mode of operation. So this is correct. Then the interactive currents are the ones that flow into the grid. Wrong. The problem of interactive and common resonance occurs in L filtered inverters due to their first order nature. So this is also wrong. So what it says is that the inverters are only, so this is, if I, let's say this is an inverter, it is only connected across in L. Now what will happen is, this is a first order circuit, and if it is a first order circuit, the resonance needs to occur between two power energy storage devices, right? Since it's only L filtered, the current L only stores energy, right? So if let's say it is supplying energy, it will just store, but it will never supply. So that is what we want, right? Resonance happens between give and take of power, right? Power flows from one energy storing devices to another. Let's say LC. LC witnesses, and if let's say it had been LC, this would have witnessed the resonance. Resonance is applicable here. Why? Because power will flow from here to here. So resonance is occurring, but not here. So this is wrong. All are incorrect is also wrong. So the correct answer is A. Select the correct statement. Nonlinear loads induce harmonic in the systems. Correct. Nonlinear loads cause harmonics. Harmonics can cause interface with transmission, telecommunication lines. Correct. Because they are high frequency in nature, and because they are high frequency, they can contribute to EMI, electromagnetic um, radiations, and that is why they will create and interfere with the telecommunication. DVR is a power quality mitigation technique. Correct. DVR are nothing but dynamic voltage regulators. So what DVR, I mean, they are not regulators, but these can be called regulators or restorers. Let's go with restorer. Since they can provide an effect over voltage, so they can act as a power quality mitigation technique as well. All are correct is the correct answer, because all of these statements are correct. 10th, for an inverter with LCL filter to be stable, it is required to ensure the stability of interactive and common currents. Interactive currents, common currents, or inverter with the LCL filter is always stable. Although in my lecture I talked about stability of interactive current, but let's say the poles of the common current are also not stable. So what will happen is, they can also produce an effect over your system, because if the poles are not stable for the common current as well, the system is unstable. So the correct answer is both interactive and common current. Right, so these were the MCQs that I wanted to discuss today. I hope that you could have gotten anything of value from this lecture. I mean, you can always go ahead and rewatch the lectures available on YouTube. I would be very happy to respond to any queries you have. I mean, since a lot of you are not joining the lectures, I hope that it's not because of, you know, it's not because of my teaching. I at least hope. I mean, I don't know if I'm doing a good job, but yeah, I mean, I would love to see you all in the next class, if at all you can come. I mean, that would be very good. So that is all for today. I mean, I hope you stay happy, stay healthy. I wish you all for your exams. There are only 2 more weeks remaining. So see you all in the next lecture. Bye bye.